All right. Good morning, everyone. Welcome back to Math 161. Friendly reminder, as friendly as you can possibly be about this, that you do have a test going on today or tomorrow, whichever day that you prefer it. It's going to be very similar to the previous test. It does have a few less questions. I don't know if I've mentioned that, but it's not a 20-question test because the material from Chapter 3 is so lengthy with most problems. The process of finding your rational zeros, the process for this, the process for that. I mean, I don't want to go into all the details right now, but we've seen some pretty lengthy problems. So doing a 20-question test in that kind of time limit of 2 hours just isn't really reasonable. So I think it was 15 questions, but don't quote me on that. Please remember that 3.5 and 3.7 homeworks are due today, and that all of your Chapter 4 homework is going to be due on May 4th. I might have that date as May 5th as a placeholder in my math lab, but it will become May 4th. May 5th was just the original placeholder date, and that our final exam is going to be on May 4th. That will be the last official day of class. We will not meet that day because you'll be taking the final because I'm only giving you 1 day. I have to allocate the class time for the final exam, and I can't give 2 days for a final. So you have to make sure that you take that final exam that day. If you have something going on, let me know ahead of time and we can reschedule, but you can't take it late because I'm going to have to put in grades into SIS within 24 hours of that final exam being completed. There is a review for test 3 that should be that's been visible for a while. That's under the assignment list. And then there is a review for the final exam. I believe I made that visible yesterday. And the final exam is going to be 25 questions. You'll be allowed your calculator just like you were with test 3. But remember, for both test 3 and the final, you are required to show your work. You are required to number your problems and then submit them into Canvas into the appropriate spot within 15 minutes. I would like it if your name is on each piece of paper as well, but it's not the end of the world since the files you upload are dedicated to your name. It's just one of those kind of final checking points, I guess, if you do that. Then remember, if you want any partial credit, email me, let me know which questions. Make sure you say Math 161 in the email title. Don't just say test. Make sure you say Math 161, please and thank you. Now, you might be wondering why I was about 2 minutes late for class this morning. I was setting up the video that I recorded, and for some reason it turned out blurry. I've never had videos turn out blurry before, so I don't know what my computer's doing. However, what I was able to do, I didn't want to just show y'all a blurry video, and I know I've said this before, but I've got a bunch of things going on, so I can't just do the whole class live. I have to have this pre-recorded stuff to be able to answer your questions at the same time, blah, blah, blah. So I just dug up a video from the semester before. So we're just going to kind of start in the middle and end almost at the end of that video because it was a longer class. If you hear me say anything about dates that don't make sense, just completely ignore them. I don't think I did. I scanned it as much as I possibly could in the 5 minutes before class, admittedly. But again, this was just a last second hiccup. I think my computer was just, I don't know, had a case of it's too early to make a silly joke. I can't come up with it on the fly. So anyways, let's go ahead and get into that. Here are the graphs for our basic exponential functions. If the base is bigger than 1, we have exponential growth. It goes through that 0, 1. It starts growing quicker and quicker and quicker on the right. It flattens out on the left. Here's the graph for exponential decay, which does the exact opposite. If you were going backwards in time, you'd say you're growing as you go backwards in time, and then it's flattening out or decaying on the right. But we give them the names based on what happens as you go forward in time, as you move right. They had those horizontal asymptotes at a height of 0, and again, they had that 0, 1 point that they all go through, which we used to do our transformations. You also had to do the transformations with the asymptote. Why am I bringing these up? Because now what we want to do is get the graph of logarithms. So as a reminder, because, let's zoom in a little now since I don't need as much, because logs are inverses of exponentials, we can swap x and y coordinates of the graph of an exponential to get the graph of a log. So I'm going to do this kind of small. And then I'm going to put both the exponential and the log in one picture. And then I'll just do the log by itself. So here's the growth if the base is bigger than 1. We go through that point of 0, 1. We have the growth on the right and the flattening out on the left. And the asymptote, which is horizontal. So let's just flip everything about x's and y's. So this point right here is 0, 1 originally. You go left, right, 0 and up 1. So that means when you invert it, that point will be 1, 0. Now, I don't want to have to go through back to the table of values and invert every single one of these by hand, the 1/8, comma, negative, if the base was a 2, that is to say, 1/8, comma, -3, 1/4, comma, -2. I'm just going to think about this more in terms of a reflection. Too far down. Here we go. So we had mentioned previously that another way to think about inverse functions is that they're a reflection about the line y equals x. So there's the line y equals x. So we're going to reflect this graph across that. So this movement that's going right kind of slowly and up really quickly, that means we're going to go right really quickly and up really slowly. So it ends up looking like this. And yes, I know that's not a perfect looking reflection. I'm doing the best I can. Then our horizontal asymptote for the original exponential function becomes a vertical asymptote for the logarithmic function. And that flattening out on the left side now is going to become almost a vertical line as we approach the asymptote. That is how we develop the graph of the log base b of x, if this black graph was the graph of b to the x. And that's if the base is bigger than 1. So exponential functions have rapid growth, logarithmic functions have very slow growth. Exponential functions have a horizontal asymptote of 0 as you go backwards. And again, this is always if the base is bigger than 1. Whereas logarithms can't even go into the negative region of x. They have a vertical asymptote of 0, and then they just stop. And again, if I was a perfect artist, you would be able to tell that the black and the red images are mirror images of each other across that line, y equals x. If your base is less than 1, which was the exponential decay, so we went through the point 0, 1. We had that, again, if you think about going backwards in time, growth on the left, and then the flattening out on the right with that horizontal asymptote. So that was b to the x, but now the base is less than 1. It also has to be bigger than 0. So now if we take this thing and we flip it up about the line y equals x, this is our mirror. The 0, 1, again, goes to 1, 0. But that horizontal asymptote that was on the right now reflects across the blue line to go above instead of below. And then this rapid growth on the left is going to become slow growth on the bottom. So here's what it ends up looking like. And it can be a little more challenging to see this reflection. That's too flat. Too many times. There we go. There we go. Again, it might be a little tougher to see. It might be a little tougher to see that reflection there, but it is there. So now, without all the nonsense, let's just get the graphs of the logarithms by themselves. So just the logs. Colon. Black. Okay. Scroll. Thank you. So if your base is bigger than 1, you go through that 0, 1 point. Slow, very slow graph, kind of looks like a, so slow growth, kind of looks like a square root graph. And then we have that vertical asymptote of y equals 0. So this was log base b of x, where b is bigger than 1. And again, you can see the red image here is just now the black image here. Same thing here. I'm going to get this red image just by itself. So we have that 0, 1 point again, with slow growth below on the right of that point, kind of like a square root that's been reflected. And then that vertical asymptoting to y equals 0 to x equals 0. I need to correct that over there. I wrote this as a y equals 0. Vertical lines are x's. That's an x equals 0. Please make sure you catch that. That's vertical line is x equals 0, the same as this one. So this is still the graph of log base b of x, but now the base has to be between 0 and 1. Admittedly, we really don't study this type of graph extensively in this course. But I still need to introduce it so that you can see the inverses of both types of exponentials. This is a much more common logarithm dealt with in research and in calculus. So expect to see this one a lot. I don't really want to say you'll never see a base between 0 and 1 for a logarithm and have to graph it, but it's just not as applicable. The main reason it's not as applicable is because it tends to put us into negative values, and for a lot of things that we model in the real world, we're only interested in positive values. Again, I said a lot of the times, not every time. Move it back down, move up to this stuff. All right, give you about 10 more seconds. Remember, you can always go to the video if you miss anything. And you're welcome. Okay. So again, that was how we created the graphs of the logarithms. This was them by themselves. And again, you don't need to memorize some 7, 10, 12, 50 point method, just a basic shape. Slow growth to the right, vertical decaying at x equals 0 to the left. You can shift these, you can reflect these, you can do all of that stuff. In the interest of time, if I had one more day to lecture, we would practice that stuff. I will not test on it. I'll only test on shifting and reflecting exponentials instead of logarithms, but I still need you to have seen these. Now, earlier, I did something that was almost a mistake when we were here. I almost forgot to write my 5 as a base. And you would have gone, well, hey, what's the base? Well, you know how if we don't write an exponent, there's an assumed number? Or if we don't write a coefficient, there's an assumed number? Or if we don't write a 2 for a square root, it's assumed to be a 2? Well, if you don't write a number for a base on a logarithm, there's an assumed number. So let's talk about that. The common log and the natural log. So common log first. The common log is used for when your base is 10. If your base is 10, we call that a common log. We call it a common log because we see it a lot of the times. It's very common. So we don't write the 10 because we see these things so very, very often. I want to write f of x first. Sometimes the undo takes a couple times to actually work. There we go. If you do not see a base written, you are making the assumption that it's a 10 if it says log of whatever. Log of 10, log of x, log of y, log of x to the 70 million. If there's no base written, it is implied to be 10 in this format. Notice I kept saying in that format. because there's another one of these. There's the natural log. And this is when the base is assumed to be, natural. Why does that word sound familiar? I feel like there was a context last class. Oh yeah, the natural number e, that 2.71828. So in nature and other things besides nature as well, when we talk about just anything that's compounding continuously, remember that whole snap of the finger, we've seen 10 bajillion bits of growth. It's just they're all so tiny. You don't really notice it in a microsecond, but it relates to the real world tons. So because we see these things so much, especially in nature, they call it the natural, we're going to have a second type of logarithm where we don't write the base. And it looks like this. And this annoys a lot of students at first. It may have even it may have even annoyed your teacher the first time you saw it, admittedly, many, many, many aeons ago. But these are two very important things. We deal with tens all the time because we have 10 fingers and toes, typically. So that's why our whole world is based on tens. If we were all born with, say, 17 fingers and 17 toes, we would live in a world where everything was counted in 17s. That's why computers count in zeros and ones, or 0 up to F, which is hexadecimal. So you have letters that are numbers because they have, I guess, 2 fingers and toes and 16 fingers and toes. The analogy falls apart there, but you get the idea. There's different ways to count. Nature counts with this letter E. So if you see LN instead of LOG, if there's no base written, it's assumed to be an E. First of all, you should never use ln if the base is an e. This is the only time you should ever use ln. You should never be writing ln 7 of x. There is no reason to ever write that. Just write log base 7 of x. Because ln and log are implying the same operator. It's just if you see ln, that is implying, hey, the base should be an e. So guess what ln stands for? Log natural, aka the natural log. English language is one of the few languages that puts the adjective before instead of after. So log natural means natural log. So again, if you never see a base written, it's either a 10 or an e depending on how we spelled out the logarithm portion, log for log or log natural, ln. So let's try this out with example, what are we up to, 4? Yes, example 4. Simplify. For A, we're going to have the log of 10. So I just wrote log of 10. I did not write a base. So we know, because I did not write a base, this number is implied to be 30 million, right? No, 10. So there is an imaginary or an implied little 10 here, and I'm going to erase it. I'm just showing you that, hey, that's a 10 because I don't see a number there. So the log of 10. I don't know what to do with this. I mean, you haven't given us any rules if the base isn't there. No, I technically didn't give you the rules if the base isn't written, but I did give you the rules no matter what the base is. These 4 properties still play out the same whether you write the base or not. So if you don't write the base, it just means, hey, it's 10. So this is log base 10 of 10. The base and the inside match, and if you remember, that was the top left property, which hopefully you still have written down in your notes. That was equal to 1. When the base and the inside match, the whole thing is equal to 1. B. I don't know why I put it there. Doesn't technically matter. B. The log of 1. Log of 1. So again, didn't write a base. It's assumed to be the number 10. Now, when there's a 1 inside of your logarithm, it did not matter what number this was, whether it's a 17, a 34, or a 10. This whole thing was equal to 0. When 1 is the inside, the whole thing is equal to 0. That's it. C, the ln of E. Doing math without even seeing any numbers. Isn't it fascinating? The natural log of E. So because I used ln, that is implying that there's a number right here. The number that is implied to be here is E. And then these two things match. It's actually the same type of setup as example 4a. So again, because there's an E implied to be here, the base and the inside match, which means the whole thing is equal to 1. It just got very dark in my house. Wrong color. D. This was the ln of E to the 5th. So again, I did not write a base, so it's either 10 or E. Don't flip a coin. Pay attention to the type of logarithm it is. It says, hey, because I wrote ln, that base is implied to be an E. So there's an imaginary little E right here. So we have a base of E with a logarithm of an exponential. Well, as long as the bases match, then everything cancels out, right? Well, this is an E, this is an E, so everything cancels out. And the whole thing is just equal to the exponent, which is that 5. Example E, not the number E. Log of 1,000. So there's no base written because it's an log. The base has to be a 10. There's an implied 10 right there, but I don't like keeping it, so because you won't see it written until you write it yourself. So there's an implied 10 right there. All right, well, that's a 10 and the inside's 1,000. Those don't match, so the answer is not 1. The inside's not just a 1, so the answer is not 0. And this isn't the logarithm of an exponential, ... yet. Because we can rewrite 1,000 as a base of 10. 1,000 is just 10 to the 3rd because there's 3 zeros. So we should rewrite this as the log, again with an assumed base of 10, and then the exponential part will now be 10 to the 3rd. Now, because this base is a 10 that you don't see, and this base is a 10, all of that jazz cancels each other out, and you're left with, once again, just the exponent, and that is 3. So the log of 1,000 is 3. Remember I told you that logarithms have very slow growth? This is the 1,000th whole number you can put into a logarithm, and the output is 3. So you're 1,000 numbers down the line, and the answer is 3. That is growing slower than any type of radical you can think about. The square root of 1,000, it's not a number you can actually do off the top of your head. The square root of 100 would be 10. That's only 100 is only 1/10 of the way to 1,000, and our answer is already bigger than the log of 1,000. So while exponentials are very, 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 very quick growth, logarithms are very, 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 very slow growth. I may have mentioned something called the logistic curve in passing last time. So a lot of people like to talk about the coronavirus and how it is going through this exponential growth. And that's only partially true. It's only partially true because it is going through exponential growth at first. But because we have a population cap, there's only so many people that can actually get the coronavirus. Eventually the growth has to slow down the closer and closer we get to, say all the people that can get it getting it. So instead of just seeing this explosion constantly, what happens is it explodes for a while, but then it starts to taper off and it flattens out in terms of the total number of people that have gotten it until you eventually just come really, really, really close or exactly hit the maximum. And this is known as a logistical curve. It is a combination of exponential and logarithmic growth, basically. So we don't study that in this course, but it is a fascinating field of mathematics that I love, so I at least like to give an introduction, because pre-calculus is supposed to be an introduction to fascinating concepts. Right, I got a few more to do. We did A through E, so we're on F. Let's go back to the black. The natural log of 1. Natural log of 1. Well, the inside's a 1. It doesn't matter what the base is. So the answer is 0. That was the bottom left property from previously. One last one. The natural log of these, that is to say, of 1 over e to the 6th. That's the natural log of 1 over e to the 6th. All right, well, we have an exponential inside of a logarithm, so the usual idea is to try and get those things to cancel each other out. Well, this has a base of an e, and the implied base that you don't see written here is an e. So if you say this is equal to 6 because that's exponent to 6, that's not right. You're going too quick. This has the same issue that this example had, the 1 over 25 inside of a log base 5. You're going to have to, well, you don't have to do the rewriting. It's already in exponential form, but you need to take that base from the bottom, bring it to the top, which will change its exponent sign, and then all of the stuff can cancel each other out. So we have to do the same thing here. So we need to write this as the ln of e to the negative 6. And I'll write it in parentheses just for consistency, but it technically is not necessary. Now the base is still implied to be an e right there. And the base of the exponential is e, and it's not in a bottom. So we can say this whole thing is just equal to the exponent, which is the negative 6. There are not a lot of good ways to guess the output of a logarithm unless it happens to fit these nice forms. So you can take the log base 10 of 100 pretty easily. You can write the 100 as 10 squared and the answer is 2. You can do the log base 10. So this was the log base 10 of 100 is the log of 10 squared, which is 2. You can do the log of 1,000, which we already saw the work for that. That was the log of 10 to the 3rd, which is 3. You can do the log of 10,000, which is the log of 10 to the 4th, which is 4. You can do the log of 100,000, which is the log of 10 to the 5th, which is 5. Look how slow these things grow. It takes an extra factor of 10 to get to the next whole number in an output. And if you ever look at any research, you may actually find some graphs. They'll say that they're done as logarithms. And I'm not going to get into what all that implies for now, but you might see a linear growth. And if it's a logarithm, that actually means that it's growing very, very, very fast or very, very slow, depending on how they're approaching the problem. But the point of this is, all right, if I wanted to say the log of 125, it's somewhere between 2 and 3. I don't really have any idea what it is. I'd say it's probably closer to 2 than 3, but I can't just guess that. I would need a calculator. Let me, if the screen just went away, don't worry, it'll be back in a second. 10 seconds maybe. Come on. Won't let me minimize my screen. There we go. And then the Word file. All right. So I've mentioned that you can put logarithms in calculators, but not always. Let's see if these are true. Let's see if our calculator agrees. LOG, oh, right here on my TI-83. If you can't find it on your calculator, Google it. So the log. Now, that just says log. If I type 100, what happens? So that just says the log of 100. I'm going to bet it's probably implying that the base is 10. I got an answer of 2, so that seems to make sense. How about the log of 1,000? 1,000. 3, yep. So my calculator, when I hit the log button, it's assuming the base is 10. Right below it is an ln. If I hit ln of 1, we get 0. If I hit the ln of e, which is the second and then the division key on my calculator, I get that, 1. If I did the ln of e squared, the natural log and the e should all cancel, and this thing should just be a 2, and that works. So you have a log base 10 and a log base e. Guess what? That's it. That's all your calculator can do up front. So maybe you were trying to check this one, this log base 5 of 1/25. You wanted to say, well, I got an answer of -2, but I'm not sure. Let me put it in my calculator just to confirm. Well, right now, I haven't taught you the way to put that in your calculator. You cannot create a new base of a logarithm in a standard scientific and graphing calculator. I'm not going to say you can't do it for every graphing calculator because there are a lot of better calculators than a TI-83. This is ancient technology. But your general scientific calculators and the scientific calculator, scientific and graphing, they can only handle bases of e and 10 for your logs. But guess what? There's a workaround that we'll learn in the next section that we can guarantee, we can check that log base 5 of 1/25 is actually -2. So that closes out section 2. Section 3 is properties of logs. Properties of logarithms. I think my favorite moment in class ever was probably, I said properties of logs, and a student started singing What Rolls Downstairs and Over in Pairs Over Your Neighbor's Dog. If you don't get the reference, look it up. It's just silly. All right, so another case of face value. We're going to give you these without any official proof. I'm not even going to do an air quote proof for this. Just take it at face value. Go to your textbook, go to the internet if you want to see proofs for them. These are a little more twisted, admittedly, in terms of actually doing a proof. The algebra is more intense. So we're just going to give it at face value. So I really think this section should be titled More Properties, since we already gave you some properties previously. In particular, these 4 properties, very, very, very important. Some students would argue that that's 12 properties because you could write these 4 properties without any of the little b's, and then it's implied that those are 10s. Or you'd have to write it on this one, of course. Or you could write these as ln's, and then you'd have 4 more properties. But it's not 12 properties, it's just 4, and then some special cases of them. If you need to write out the special cases separately, you can, but these 4 take care of everything. So I think that's good enough. But you've just got to remember, if the base matches the inside, the answer is 1. If the inside's a 1, the answer is 0. If you got logs of exponentials or exponentials of logs, if you can make the bases match, or if they already match, the answer is the exponent or the inside of the log, whichever the case is. So 4.3, more properties of logs, first up being the product rule. The product rule says that, I'll keep it in red, log base b of a product, sum m times n. It doesn't have to be letters m and n. This is equal to the log base b of m, then a plus, and another log base b, and then of the n. Hey, Rambo, it's okay. My dog doesn't like storms. He just came to greet me and get under my feet. Okay, so that's your product rule. We call it a product rule because it's the product of a single logarithm. You can actually separate this into an addition of 2 different logarithms, but the bases have to be the same. You can't make the base of one a 7 and the base of the other a 9. They have to all agree. Next up, we have the quotient rule. And this one follows completely logically, or logarithmically if you want a terrible pun, to the product rule. A product led to a sum, so guess what? A quotient, a division, ends up leading to a subtraction. These are very, 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 very important. Those colors don't clash too much, I hope. You are supposed to memorize them. You will see them littered throughout calculus, et cetera, usual spiel. So when we're dealing with logarithms and there's multiple arguments, multiple numbers, multiple variables inside of it, or separate logarithms, there are times when it's better to have separate logarithms. There are times when it's better to have just a single logarithm. It depends on what your goal is, and math typically works as a grass is always greener. What you see is usually what you don't want. So if you see the product version, you need to probably separate it as a sum, and vice versa. If you see the sum of two, you combine it as a product. Now, this rule does not work the other way. A log of a sum is not a product of different logs. So please note that this does not work the other way around. I can't do, and I'm going to erase this because you can't do it, and I don't want to have it stuck on here. And I can't write with a highlighter. So the log base b of m plus n inside of a single one, this is not the same thing as the log base b of m times the log base b of n. Again, this is complete trash. I'm going to erase it. And the same goes for the quotient rule. You can't flip-flop which one's a difference and which one's a quotient. It only works one way. The proof, again, you can kind of convert these things to exponentials. It's a little weird. It's not terrible, but let's just take it at face value and try it out. So example 1. How are we doing on time? 30 minutes. And we're going to expand. So the left side of these is the condensed version. In fact, let me just give myself a little more space. Just a little more space. So the left side is the condensed version. The right side is the expanded. Condensed means you don't have to take up nearly as much space. Expanded means you get the picture. Now we'll do example 1. And the instructions were expand, I believe. Yes. Expand your mind, expand your logarithm. And we're going to do log of 4x. Oh, Mr. Beckner, you forgot to write a base. No, I didn't. Means the base is a certain number, 10 or e, in this case, 10. So to expand, this is a product. This is 4 times x. I didn't write a dot in here originally, but for emphasis, I will. You don't have to have this in parentheses. You don't have to have all these extra little details. Just by writing 4x, that says that 4x is inside the logarithm. If I wanted the x outside the logarithm, I'd have to do this, which is all kinds of weird, but I'm not saying you never see it. All right, so this is a log of a product. So for some reason, maybe we have a reason to expand this besides our teacher just saying expand, but we're just practicing that for now. So the base is a 10, so we're going to make 2 logarithms with a base of 10, where the first one will have the first factor and the second one the second factor. In other words, don't overthink this. It's the log of 4 plus the log of x. And for now, that's all we're doing. I like introducing this problem because this is not technically the simplest form of the answer, but all I said was expand, so at least it still applies. We're going to circle back to this problem later to actually show what the true answer to this is in simplest forms. In simplest form, not forms. B, let's do the log of 100, y. So base, once again, is implied to be a 10. You're going to see me do lots of logs and ln's because bases of 10 and e are the most common in the world. Okay, so that's 100 times y, so we can separate this as a sum of 2 logs. Log of 100 plus the log of y. Now, if you stop here, you would get an incorrect answer because this is simplifiable based on rules we've been taught thus far. The log of 100 is simplifiable. So I'm just going to drag the log of y along, but you might say, well, how do you simplify it? This base is a 10, this is 100. Well, I literally did that example earlier in this red right here. You just got to make that 100 a 10 squared, then the 10s and the logs all cancel and you get just a 2. That's that top right rule or top right property from the previous section. So I'll show all that work though, don't worry. So that's the log of 10 squared. Remember, if these don't match, if you can't try a property, try rewriting them with common bases. So that base was a 10, so I tried to write 100 as 10 to some power, which is 10 squared. Then our plus log of y, but this log of 10, log base 10 of 10 squared, everything cancels except the exponent. So the first term doesn't even have a log. And let me tell you, this is the number one mistake that students who have decent knowledge of logarithms, but not perfect knowledge, this is the number one mistake they make. They stop here, and then they get it wrong. That is not the answer because the log of 100 is simplifiable. So you have to be on your toes. When you see numbers inside of logarithms, if it doesn't immediately use one of those properties, make sure that you can't rewrite that as a matching base because then you could apply one of those properties. All right, C, the natural log of E over, let's do Z. That's a Z in the bottom. Remember my Z's, I put a line through the middle. I saw a question. Could we not have made the 4 a 2 squared in the previous example? So, Jonathan, that is an excellent observation, and that is exactly what we want to do later. So what someone just asked, and I didn't want to mention it, but since someone did, I will now. This is going to involve what we'll circle back to later. 4 is 2 squared. Now in B, it was beneficial to us because when we wrote 100 is 10 squared, the bases matched. So all that jazz canceled. If you write 4 as 2 squared, the base is 2, but the base of the logarithm is 10. There is no way to make a 4 have an exponential base that matches 10. So that's why for now, writing this as 2 squared isn't helpful, but later when we learn another rule, another property, we will want to write that as 2 squared and it will help us simplify it. So that is a great observation. And again, we'll circle back to that. All right, so back to C, the natural log of E over Z. So because that's a division, that's the quotient rule. We're going to separate that as a subtraction. Now, I want you to pay attention to the m and the n's placement in all of this because it's important. The m was in the top of that fraction, and it is then a positive logarithm. I didn't write this, but there's a little plus sign here, imaginarily, right? So the m came from the top, and that makes it a positive logarithm, whereas the n was in the bottom, and because the n was a bottom, that's what makes this a negative logarithm. And guess what? That relates to previously we were bringing bases from the bottom with positive exponents to the top and making them negative exponents. It has something to do with that. So again, anything that comes from a top is a positive logarithm when separated, when expanded. Anything that comes from a bottom is a negative logarithm when expanded. All right, so natural log of E over Z. The E is in the top. So that's a natural log of E. That's positive. The Z is in the bottom, so that should be a negative logarithm. So the natural log of Z with a minus preceded in front of it. So that's the expanded version. And if you box it up, it's wrong. Another one of those. A lot of students make it to this point, stop, and then they made a mistake because they didn't simplify as much as possible. The natural log of E, remember this little base right here, we don't see it, but it is E. They match, which means that whole first bit just turns into a 1. Not a natural log of 1. Remember, those properties were about getting rid of the natural logs. So just like with B, we're able to completely eliminate a logarithm from one of the terms. Maybe that's a reason to be expanding things. Maybe being able to do this is helpful. If I were asking you to graph this natural log of E over Z, this is exactly what you would want to do because it gives you a shift and a reflection. This is a vertical shift of up 1 and a vertical reflection because all those are outside the core. Whereas how would you know how to graph the natural log of v over z? We know how to graph logs of x, or whatever letter, a log of y, a log of z, but not if the z's in the bottom. I didn't tell you how to do that. Well, it turns out it's a shift and a reflection. All right, D. So that's one thing that expanding is good for, it's graphing. Also, when you get to calculus, when you have to do things like derivatives and integrals very often, it's helpful to expand logarithms as well, but that's not for us. Not today. Log base 2 of 4x over yz. Again, that's another z in the bottom. So this has got more than 2 things inside. I didn't tell you what to do if there's more than 4 things inside. That doesn't matter. All these rules say is if you have a multiplication, separate them with an addition. If you have a division, separate them with a subtraction. So because I got multiple bits in the top, multiple bits in the bottom, it doesn't matter. Anything that comes from the top is going to be a positive logarithm. Anything that comes from the bottom is going to be a negative logarithm. Now I'm going to spoil something up front. I'm going to write this incorrectly at first. I'm going to do most everything correctly. I'm going to be missing a detail that I'll put in later. So I'm going to pretend to make a mistake right now. So log of 4, the 4 is in the top, so that's a positive logarithm, plus log of x, the x was in the top, so that's a positive one. The y and the z came from the bottom, so they should be minuses. Minus log of y, and then a minus log of z. So there's a mistake in here. The mistake is the original log had a base of 2. And a lot of people get, oh, these are all 10s and e's, all 10s and e's, all 10s and e's. So then when you see the 2, you just drop it. No, these are not 10s. They're supposed to be 2s. They all have to match. You have to be consistent with what the original base was for this. Now, when your argument's a variable, the x, the y, the z, you can't do anything to these last 3. But look at this first one, log base 2 of 4. Someone mentioned earlier, hey, 4 is 2 squared. And it didn't benefit us in that A problem because the bases didn't match, but it will here because they do. And again, when I say don't benefit, again, that's for now. We'll learn something soon. So let's rewrite that as the log base 2 of 2 squared. And I'll put that in red to show you what I changed. This was the only thing that changed. Everything else stays the same. So log base 2 of x minus log base 2 of y minus log base 2 of z. And the reason we do that is because if we hadn't, we might have boxed it up and it was wrong because log base 2 of 2 squared, all of this stuff, because the bases match, cancel, and you just are left with the exponent, which is that red 2, outside what I circled. But then we have the plus log base 2 of x minus log base 2 of y minus log base 2 of z. That is our answer. So these 4 examples were us practicing expanding logarithms that had products or quotients inside of them. There is one more property that pairs well with these, and it's the power rule. So we had the product rule, we had the quotient rule, and now we have the power rule. And the power rule states that, and again, once again, face value, no proof, the log with a base of something with an exponent, and we'll do P for power. I don't want to use E for exponent for obvious reasons. So if you have a logarithm, no matter what the base is, if inside of it it's exponential, if the base of the exponential and the base of the log don't match, so these 2 things don't match. This is a B, this is an M. So this is kind of like that scenario with the log base 10 of 2 squared that's inside of this. What we can do is, and this is really, really cool, we can bring the exponent out front as a multiplier of the log. So that's P, not plog. That's P times the log base b of m. So this exponent has been brought out as a coefficient. If I space, is it going to mess anything up? It doesn't. Good. So the exponent has been brought out as a coefficient. The left side is the condensed version. The right side is the expanded version. Now, the condension and the expansion of these is pretty obvious, I think, because this looks like a lot less space condensed. This looks like a lot more space expanded. I don't really see a reason why this one's condensed and why this one's expanded. Condensed means you have as much stuff inside of a single logarithm as possible. That's the true meaning of condensing for logarithms. It means you have everything possible inside of it. So the expanded version, there's something that could be in it, but is not. Now again, there are times when expanding is beneficial. There are times when condensing is beneficial. It depends on the scenario we're thrown in. Right now, we're just practicing how to go back and forth. So far, we've only expanded and none of this at all. So let's practice that. So example 2. Expand. Expand your logarithm. We got the log of x to the 4th. The log of x to the 4th. So to expand this means we don't want to see any exponents inside the logarithm. Now, we would first try and say, oh, well, if the bases match, then everything cancels and the whole thing is just equal to 4. But this base is a 10, this base is an x. They do not match, so that property from the last section does not apply. However, we have a new property that we can use, which I want to highlight like the rest. So what we're able to do is take this 4 and bring it out front as a coefficient, and then everything else just stays the same. And that's it. That's the expanded version. Now we have just a log of a number or a log of a variable without an exponent. Having exponents inside of logarithms complicates things. Having just a number times a logarithm, that's a lot simpler in terms of a concept. But again, just because the left side is more complicated doesn't mean it's not useful. It is quite often useful. Let's do another one. Let's do the log of 4, b. Oh, well, this doesn't apply. I don't see an exponent. Well, you don't see it, but you certainly can write 4 as 2 squared. I wonder if anyone's picking up where we're going with this. So that 4 we can change as 2 squared. And in fact, I'm going to do the exponent in blue for emphasis. So when you have a logarithm of an exponential, if the bases don't match, see this base right here is a 10. They don't match. But that doesn't mean we can't do anything necessarily. We can take the exponent and bring it out front. So there's our 2, there's our exponent 2. And then we have our log of 2. Now, in terms of numerical simplification, this is simpler in the same way that a square root of 8 is simpler by writing 2 square root of 2. Or a square root of 50 is simpler by writing 5 square root of 2, because there are things we can do with 5 square root of 2 that you might not be able to do with the square root of 50 if we're trying to combine it with other stuff maybe. So this is what makes example, was it 1a? Yes, 1a simplifiable. So going back to 1a's answer, which was log of 4 plus log of x. Well, now we know the log of 4 is 2 log of 2, so we can rewrite this as 2 log of 2 plus the log of x. It doesn't look simpler, but in terms of mathematical operations, there would be things you can do with that one that you can't do
with log of 4 necessarily. Often. Not every time, often. All right. C. The natural log of 7x to the 4th over y to the 3rd. This is combining everything we've seen in the section now, the product rule, the quotient rule, and the power rule. So we're going to have to make several logarithms. We're going to have to take exponents out. You want to do the exponents last. You need to handle the separation of pluses and minuses first, because with two exponents of 4 and 3, which one goes in front of the logarithm? Well, honestly, neither, because there's also an exponent of a 1 right here that you don't see. And if you got different exponents, you can't bring it out. You can only have everything raised to a single exponent. So let's separate this into multiple logarithms. The 7 and the x to the 4th come in the top, the y to the 3rd is in the bottom, so the y cubed is a negative logarithm. So this will be the natural log of 7 plus the natural log of x to the 4th minus the natural log of y to the 3rd. 7, I don't really think we can write that as a base besides itself. So that's as far as we can take that. If it was an 8, we'd have to change it to 2 cubed, because then we could take the 3 out front. If it was 100, we could write it as 10 squared, and then the 2 could come out front. But the second and third logarithms have exponents, and we can bring them out front. So that's a plus 4 natural log of x minus a 3 natural log of y. And that is as far as we can take that one. One more like this, for good measure, the natural log of 100 over e to the 3rd times x. So again, we're going to have to handle the exponents last in this process. So that's a natural log of 100. 100 was in the top, so that's a positive. Minus the natural log of e to the 3rd, because it was in the bottom, minus a natural log of x. Okay. Well, the natural log of 100, we can't simplify just that, but we can rewrite the 100 as 10 squared. It may or may not benefit us, right? It probably will. So there's the natural log of 10 squared minus the natural, let's leave everything else the same, natural log of e cubed minus natural log of x. Now let's handle the exponents. So the 2 and the 3 will come out front. There's nothing to be changed with the x. There's a 1 here, bringing a 1 out front doesn't really change anything. Oops, too far to the right. So that would be 2 times the natural log of 10 minus 3 times the natural log of e minus the natural log of x. Natural log of 10, we can't do anything with that. The bases don't match. E doesn't match with 10, so that's it. Some people say, oh, okay, well, we're done now. Nope. Look at that. The 3 doesn't have any effect on anything, but the natural log of e is simplifiable. Remember that the natural log of e is 1. Because the bases in e, they match, so the whole thing basically cancels with a factor of 1. So this would be equal to 2 times the natural log of 10 minus 3 times 1 minus the natural log of x, which is just 2 natural log of 10 minus 3 minus the ln of x. And that's our answer. Now, I want to show something else. I want to show this problem done a different way, starting right here. So starting right here, the ln of 10 squared minus the ln of e to the 3rd minus the ln of x. Now, in the black ink, I took all the exponents out front. I didn't have to do it that way with this middle term. The first term, yeah, you have to. There's a 2, there's your ln of 10. You have to do the first one this way. But this middle one, the bases match. So you don't have to take the 3 out front and then say the natural log of e is 1. You can use that top right property from the previous section. If the bases of the logarithm and the exponential match, the whole thing is just equal to the exponent, which is 3. So then a minus 3, then the minus ln of x. The same answer. What I love about this example and why I always do it is it shows that these properties are real. They do actually function properly. Again, I never did any proofs, but I feel like seeing that one both ways just gives us a little more faith that this stuff does run accordingly. What do we have? 7 minutes. Let's do the next 1 or 2 examples and then we'll probably be done. So we did a ton of expanding. Now let's go the other way. Now let's condense, because again, there are times when we want to expand, very often in graphing, very often in doing calculus, which is derivatives and integrals most often. But when we want to solve equations involving logarithms, most of the time what we want to do is condense them. We only want to see a single logarithm so that we can then change it to exponential form, something we're more used to seeing. At least that's the usual affair. All right, so example 3, condense, obviously, condense. Let's switch my color. I didn't mean to do that in blue, not that it matters. Log of x plus the log of y minus the log of 3. So we got a problem. Maybe we were trying to solve this equation or analyze it or something like that. It's not actually an equation, I didn't write it that way. But maybe there's a reason we want this to just be a single logarithm if we can make it a single logarithm. Notice I said if. Because in order for that to happen, the bases all have to match. Well, that's a log base 10, that's a log base 10, that's a log base 10. So yes, we can condense this into just a single logarithm of some products and quotients. There were no coefficients, so there'll be no exponents here. The x and the y came from positive logarithms, so the x and the y go in the top. The 3 came from a negative logarithm, so it has to go in the bottom. And believe it or not, that's it. That's the answer. It's a pretty easy one to start with. Again, because the x and the y were positive logarithm terms, the x and the y go in the top. Because the 3 was a negative logarithm term, it goes in the bottom. If you call this a minus, if you brought that up as an exponent, now you've got an exponent of -1, which takes the 3 from a top to a, you guessed it, bottom. That's why it works. Next up, 6 times the log of x minus 4 times the log of y, probably, yes. 6 log of x minus 4 log of y. So when we were expanding, we needed to do the exponents last. Everything's flip-flop now, so we have to do the exponents first. What exponents? The 6 and the 4, these coefficients. When we're condensing, the coefficients become exponents. So this is the log of x to the 6th. The coefficient goes up as an exponent, minus the log of y to the 4th. Again, the 4 came up as an exponent. You can take the minus with it, but then you'll have to do your negative exponent rule. It's just more work than it's really worth. Now, because there's no coefficients, you can only contract these into a single logarithm when there are no coefficients written. That actually just means they have matching coefficients. So it's implying they're both 1s, but they could both be 2s, they could both be 3s, they could both be 5s. It's a little annoying to deal with because we really want the coefficients to be exponents. But there's some shades of gray there. But anyways, once you don't have coefficients, this is when you condense the logarithm. So just a single logarithm, both the bases were 10, so we can do this. The x to the 6th, that's a positive logarithm, so it'll go in the top. The y to the 4th was a negative logarithm, so it goes in the bottom. And that's all we can do. We have enough time to do C. We do have enough time. I can hear you groaning already. 3 log of 2, I'm kidding. That's my dog snoring. Minus 2 log of 5, last problem for the day, I promise, plus 4 log of x. Again, all these bases don't have to be 10s. They can be different bases, and that means, well, first of all, they don't have to all be 10s. They can all be 7s. They can all be 31s. They can all be e's. They can be any number they want. As long as they're all the same, you can condense them into a single logarithm. But there are weird, wacky problems where they're not all the same, and then you'll still have 2 or maybe even 3 logs in the answer. Let's handle the exponents first. Bring the 3, the 2, and the 4 up. So that's the log of 2 to the third minus the log of 5 to the second plus the log of x to the fourth. Well, 2 cubed and 5 squared, because we're just going to condense this into a single logarithm, we're working backwards as to how we have been doing it, feels like. Let's just write that as the log of 8 minus the log of 25 plus the log of x to the fourth. Because when it's in a single logarithm, there's no reason to see the 2 cubed and the 5 squared. It wouldn't benefit us. So now, they're all bases of 10, so we can write a single log. The 8 and the x to the fourth were positive logarithms, so the 8 and the x to the fourth go in the top. Positive log with the 8, positive log with the x to the fourth. The 25 came with the negative log, so the 25 goes in the bottom. This is our answer. And again, if you had gone straight from here to the condensed version, you'd get the log of 2 cubed times x to the fourth over 5 squared. That's not simplified. No, there's no reason to have 2 cubed in an answer. There's no reason to have 5 squared in an answer. That's why we need the 8 and the 25. All right, so last second reminders. Test 3 is on right now.
And that's the part where I was about to say a date that wouldn't have made any sense. All right, so thank you for dealing with that. I know it shouldn't have felt really any different to you, but I just kind of felt bad with that. Hopefully this situation doesn't happen again, but if it does, the good thing is on Thursday, I have the same thing. I can use material from a previous semester. We just got to watch out for dates that might not be correct. So only pay attention to the dates at the beginning of class and end of class. So again, thank you for your patience and understanding with that. But technology is technology. What can we do sometimes? So 3.5 and 3.7 due tonight. Remember, test 3 is today or tomorrow. Take it one of those 2 days. Your final exam is the 4th. All chapter 4 homework that will be assigned, which should be 4.1 through 4.4, will be due on the 4th. And yeah, so final, 1 day, no class, 2 hours, 25 questions. Calculator, make sure you have a calculator for test 3 and the final. That'll help you. Make sure you show all your work. Remember, no work means I could go back and give no credit for some of these more complicated questions, and I don't want to do that. I want you to earn as much credit as possible. So per usual, if you have any questions, please email me. Besides that, we will see you on Thursday. Take care, everybody.